Hi everyone, I'm Baihan Lin from Columbia University. I'm presenting my work, Keep It Real, a window to real reality in virtual reality. There is a saying in virtual reality that the cat problem is the ultimate unsolved challenge. Traditional VR technologies usually emphasize creating an entirely immersive environment. Visual inputs of the real realities are usually discouraged. When you are immersed inside a virtual reality, your view of the real world is obscured by the head-mounted VR device, and you lose touch to the real world. In this way, the cat can easily get to you and trip you in no time. Many studies have attempted to introduce virtual mirrors to facilitate embodiment, rehabilitation, and education, but almost all of them reflect the virtual space, i.e., the body of the avatar in the virtual room. We demonstrated in our system, however, that the introduction of such a virtual window or mirror reflecting the real world can bridge the two realities in a surprisingly beneficial synergy. Introducing a virtual window or mirror, which the user could activate and deactivate at any time, could encourage the user to actively attend to and seamlessly receive real-world feedbacks where virtual rendering is challenging. Projecting a geometrically accurate representation of user's image and reality into a movie could create an illusion that the user is presently sharing the same universe with the virtual characters. In other words, breaking the fourth wall. The projective geometry problem is outlined as follows. The user is the observer O who has a reflection of a virtual mirror image at O' from a window or mirror on a virtual plane. Camera C with unknown distance covers the user in its field angle, and we wish to solve the perspective transform, i.e. the homographies, from camera view plane to 3 space in 3 steps. 1. To the virtual camera view plane by the mirror. 2. To the virtual plane where the mirror is located. And eventually 3. To the image space where the observer sees. Solving the third homography is straightforward, but solving the first and second homographies is non-trivial because estimating depths in a video and camera at the same time is an innately challenging problem. In other words, there is not a unique homography for the projection of the mirror image, but an array of solutions for each point. We tackle the issue by introducing an additional scaling factor to constrain the homography according to each pairs of image frame. Here we summarize the steps involved in the image wrapping. First, rectify the camera feed with respect to the virtual space. Then, chop the image given a proper camera field angle, and finally project to the image space given the computed homography. These frameworks turns out to be fairly robust and flexible to apply to a wide range of applications. For instance, we can introduce a V2R mirror into a video stream or movie clip such that in every scene where a target painting appears, our camera feed is projected on it. In augmented reality, we can replace certain region in the back-facing camera field with the front-facing camera feed. In virtual reality, we can also make a post board a V2R window whenever a button on the control bar is pressed. As an important concept of AI, the sense of presence can effectively engage the interaction between the human and the virtual agent in virtual environments. Here is a demonstration of our method. As shown, the V2R can be applied to in real time in timely fashion. The orange background is actually a video clip. The red character inside is from a video webcam or phone camera. And the virtual window or mirror is wrapped onto the video corresponding to the right geometry. We see that when our viewing perspective changes, the system automatically computed the projective geometry and wrap around the camera feed to reflect that. Here are more examples in different settings. For instance, in the middle case, the virtual perspective is clearly looking down from above and left, and the wrapped image is indeed as if the observer was looking down to the left and can only see from the mirror the upper and left half of the body. Exciting next steps involve developing a wide spectrum of interactions around the V2R and accompany intelligent modules such as gesture recognition. Imagine creating a virtual window to the real world by drawing a square in the air with your hands. Video conference with virtual windows to multiple camera feeds, literally as if everybody is in the same room. Real-time rendering of virtual objects given the real-world camera feed. For instance, bring an apple from the real life to the virtual space. Another direction is to improve the projective geometry. These mirrors and windows projected from single camera 2D images are currently pseudo-representation of what one could see from the exact computed point of view in the real world, as the single camera setup makes it hard to perform a 3D reconstruction. A useful extension of V2R is to introduce multiple cameras, such that the camera depths can be properly estimated along with a 3D projection of the details that could be revealed but hidden in the 2D representation. For instance, an occlusion. These improvements could elicit highly interactive user experience and engage more users and research into the field of intelligent virtual reality interactions. Thank you for your interest. If you have any question, feel free to reach out to me. The full paper can be accessed on arXiv, and the code is available at my GitHub repository. Thank you.